Learning objectives. In this chapter, the users would learn the following aspects of Introduction to Microprocessors, Microcomputer, Introduction to Digital Computer, Microcomputer Organization, Machine Language, Architecture of a 16-bit generic microprocessor, Simplified Memory Organization, DMA, Interrupts, 8086-8088 Architecture and Instruction Set, Steps for Program Development for 8086-8088, Features of Microprocessor, Introduction to 80286, 80386, 80486, Numeric Processor 80387, various versions of 80386 and 80486, like 80386SX, 80386DX, 80486SX, 80486DX2, 80486DX4, and their comparisons. Introduction. Electronic digital computers have existed since the 1940s, but microcomputers made their advent only in the late 1970s. The appearance of microcomputers coincided with the development of large-scale integrated circuits. A microcomputer is a general-purpose digital computer which was designed primarily to handle basic day-to-day office tasks. It is a relatively inexpensive computer with a microprocessor as its central processing unit. It includes a microprocessor, memory, and input-output facilities. Microcomputers became popular in the 1970s and 80s with the advent of increasingly powerful microprocessors. The predecessors to these computers, mainframes and minicomputers, were comparatively much larger and more expensive. Microcomputer uses. Microcomputers are the most widely used computers which have found application in everyday activity of the modern world. The speed and accuracy of processing of the personal systems account for their high popularity. Think of a world where share market trading had to be carried out manually. Also imagine a situation when the fastest means of communication in olden days were telegrams and letters, not telephone and mobile phones of modern times. Though those days are not even 50 years ago, you cannot imagine life now without the aid of personal computers, or PCs as you abbreviate them. Components of microcomputer. The basic components of a microcomputer are input units, output units, memory, processor. Input units. Devices that allow you to enter information into the computer. A keyboard and mouse are the standard way to interact with the computer. Other devices include mic, scanners, microphones, joysticks, and gamepads that are used primarily for games. Output units. The output devices are how the manipulated information is returned to us. They commonly include video monitors, printers, and speakers. Memory. When you use a program, the computer loads a portion of the program from the hard drive to the much faster random access memory, RAM or RAM. When you save your work or quit the program, the data gets written back to the hard drive. Processor. The processor consists of the data path and the control unit. Data path consists of a register file and ALU. Register is a storage location used to hold data or memory address during execution of an instruction. ALU, the arithmetic logic unit, receives data from main memory and or register file, performs computations and writes the result back to main memory or registers. Decodes and monitors the execution of instructions and also acts as an arbiter while various systems compete for resources of CPU. Types of microcomputer. Personal computers remind us mostly of desktop computers or laptop computers. But there are other types of microcomputer. Desktop computers. Desktop computers are those personal computers that you come across in business institutions, ATMs, and offices. They have the second largest market among all kinds of PCs. They are unportable and long-lasting. Laptop computers. Laptop computers are personal computers. As the name goes, it is a portable computer which is usually a lightweight PC. The special feature is that it is far lighter than a desktop PC And being a wireless system, you can use it even when there is a power cut or you're away from home where electricity is not available. Handheld computers are palm tops. Palm tops, like laptops, are portable personal computers which are even smaller and lighter and can be carried in a pocket. Ideally, a palm top is used for storage of personal information like phone numbers and appointments. Nowadays, with the improvement of technology, palm tops come with colored monitors, sound recording facilities, and even provision for access to the internet. Tablet personal computers. Tablet PCs are mostly used in graphics work. It is an electronic device that utilizes digital ink to write or draw directly on the monitor of your PC. Workstations. This is slightly different from the regular PC in the respect that it has evolved from the mini computers. Originally used for engineering, graphics, and such other non-personal work or technical work, workstation computers were designed for the purpose of singular interaction of computer with one person at a time. Future of microcomputer. Microcomputer technology is still evolving. More recently, computers have been enabled to accommodate voice input and output. The development and widespread use of powerful communication tools for computers led to the mass popularization of the Internet, which is fueling another growth spurt in the industry and its technology. Continuing success in the marketplace depends on the continual development of software to make machines both easier to use and more versatile. Microcomputer software is developing in the direction of artificial intelligence. One example of this is smart business software that helps the user make decisions by analyzing data for patterns of behavior and then applying those patterns to new situations. Digital computer. A digital computer designed to process data in numerical form, expresses in binary form. What is digital computer? A digital computer is designed to process data in numerical form. Its circuits perform directly the mathematical operations of addition, subtraction, multiplication, and division. The numbers operated on by a digital computer are expressed in the binary system, such as binary digits. Bits are 0 and 1, so that 0, 1, 10, 11, 100, and 101 correspond to 0, 1, 2, 3, 4, 5, and so on. Binary digits are easily expressed in the computer circuitry by the presence 1 or absence 0 of a current or voltage. A series of 8 consecutive bits is called a byte. The 8-bit byte permits 256 different on-off combinations. Each byte can thus represent one of up to 256 alphanumeric characters, and such an arrangement is called a single byte character set. Integrated circuit. Large-scale integrated circuits appeared in the early 1970s. The development that allowed the processor to fit on a chip also allowed chips to be used for memory, replacing the expensive ferrite core memory. These advances led to the birth of the microcomputer. By the early 1970s, machines were being produced for home and office use. Of all the early microcomputers, the Apple and IBM families of machines have survived to become the major players in the market. Computer architecture. Computer architecture is a conceptual design and fundamental operational structure of a computer system. It is a blueprint and functional description of requirements and design implementations for the various parts of a computer. It focuses largely on the way by which the central processing unit CPU performs internally and accesses addresses in memory. Computer architecture. Subcategories. Computer architecture comprises at least 3 main subcategories: instruction set architecture (ISA), microarchitecture, system design. Instruction set architecture. ISA is the abstract image of a computing system that is seen by a machine language or assembly language programmer. It includes the instruction set, memory address modes, processor registers, and address and data formats. Microarchitecture. Microarchitecture, also known as computer organization, is a lower level, more concrete description of the system that involves how the constituent parts of the system are interconnected and how they interoperate in order to implement the ISA. The size of a computer's cache, for instance, is an organizational issue that generally has nothing to do with the ISA. System design. The system design includes all the hardware components within the computing system, such as system interconnects such as computer buses and switches, memory controllers and hierarchies, CPU offload mechanisms such as direct memory access issues like multiprocessing. Once both ISA and microarchitecture have been specified, the actual device needs to be designed into hardware. This design process is often called implementation. Implementation is usually not considered architectural definition but rather hardware design engineering. Microcomputer programming languages. Microcomputers are typically programmed using semi-English language statements. This is the assembly language. In addition, microcomputers use a more understandable human-oriented language called the high-level language. No matter what type of language is used to write the programs, the microcomputers only understand binary numbers. Therefore, the programs must eventually be translated into binary forms. Types of programming languages. Microcomputer programming languages can typically be divided into three main types: machine language, assembly language, high-level language. A machine language program consists of either binary or hexadecimal opcodes. Programming a microcomputer with either one is relatively difficult because one must deal only with the numbers. The architecture and microprograms of a microprocessor determine all its instructions. These instructions are called the microprocessor's instruction set. Programs in assembly and high-level languages are represented by the instructions that use English language statements. The programmer finds it relatively more convenient to write programs in assembly or a high-level language than in machine language. However, a translator must be used to convert the assembly or high-level programs into binary machine language so that the microprocessor can execute the programs. An assembler translates a program written in assembly language into a machine language program. A compiler or interpreter, on the other hand, converts a high-level language program such as C or C++ into a machine language program. Assembly or high-level language programs are called source codes. Machine language programs are known as object codes. A translator converts source codes to object codes. Machine language. Machine language is the low-level language. It is the only language that is directly understood by the computer. It does not need any translator programs. We also call it as machine code, and it is written as strings of ones and zeros. When the sequence of code is fed to the computer, it recognizes the codes and converts it into electric signals needed to run it. For example, a program instruction may look like this. It is not an easy language for humans to learn because of its difficulty to understand. It is efficient for the computer, but very inefficient for programmers. It is considered to be the first-generation language. It is also difficult to debug the program written in this language. It is very difficult to program in machine language. The programmer has to know the details of hardware to write the program. The programmer has to remember a lot of codes to write the program, which result in program errors. Along with these disadvantages, the microprocessor has the only advantage that program of machine language runs very fast because no translation program is required for the CPU. To overcome these difficulties, there are special programs called compilers which accept programs in higher-level languages and translate them into machine language programs. Microprocessor. The microprocessor is also known as a central processing unit, CPU, which is the brain of all computers. In a PC, the CPU must be powerful in order to handle a variety of peripheral devices. The first microprocessor was the Intel 4004, introduced in 1971. It was not powerful. It was primarily used to perform simple mathematical operations in a calculator called BusyCom. Modern microprocessors can perform extremely sophisticated operations in areas such as meteorology, aviation, nuclear physics, and engineering. They take very little space and are superior in performance. The microprocessor incorporates the functions of CPU on single integrated circuits. It is a multi-purpose, programmable device that accepts digital data as input processes according to instructions stored in its memory and provides results as outputs. It operates on a number and symbols represented in the binary numeral system. The microprocessor in personal computers is used for computation, text editing, multimedia display, and communication over the Internet. The 8-bit microprocessor 8008, along with the 16-bit addressing, also led to the first general-purpose microcomputers from the mid-1970s. The new processor inspired software companies to write programs, including the control program for Microprocessors operating system and the first version of the Microsoft BASIC. Features in microprocessor. Some features included on past and present microprocessors are multitasking support, general-purpose I/O pins, programmable internal timer, time processing unit, multiple cores, onboard memory cache, AES-NI encryption, decryption, integrated memory controller. Multitasking support. Some processors provide instruction in which multitasking is efficient. General-purpose I/O pins. These are connections to the processor which may be software configured as an input or an output. This allows the processor to sink enough current to drive LEDs directly from the CPU. It is used in control circuits. Programmable internal timer. It is used for sophisticated time-dependent programming. It can count up and count down flag events via the status indicator, which can be tested by the CPU. Time processing unit. It handles the event based on time and counts. It boots the processor according to the program requirement. Multiple cores. It takes care of the heat problems associated in running processes during the process. Onboard memory cache. It is the ultra-high-speed memory built onto processor core which enhances program execution. AES-NI encryption, decryption. It is a built-in encryption feature of Intel i7 which is used to reduce processing overheads when dealing with coded information and secure links. Integrated memory controller. It is memory which is embedded in the processor core along with the external memory controller chip. 16-bit generic microprocessor. 16-bit generic microprocessor interface is for device initialization, control, register, and port statistics access. It fits in many generic systems including industrial PCs, manufacturing electronic and automation, single-board computers, etc. The 16-bit generic microprocessors are those that are based on registers, address buses, or data buses. The generic microprocessor is designed using a CSIC component-based architecture. Some of the fundamental components to process diverse instruction sets are register file and barrel shifter, which are required for the working of generic microprocessors. The register file is used for temporary data storage. Most of the instructions of the microprocessors studied are from register to register or from register to memory. The instruction supplies information about the addressing mode and other related information that can be used to calculate the effective address of the operand using the effective address calculator. It is used at various stages of operation like reset, run, interrupt, etc. These stages are used according to the priorities through the priority encoder. The barrel shifter is used at the ALU output or built into the ALU for shift, rotate, as well as multiply, divide operations. 16-bit processors have been supplanted in the personal computer industry but remain in use in a wide variety of embedded applications. For example, the 16-bit XAP processor is used in many ASICs. 8086 and 8088 microprocessors are models of the 16-bit microprocessor. Two approaches. Functions of the existing consists of RISC core. Two approaches to implementing a generic microprocessor architecture were considered. The architecture functionality is a superset of the functions of the existing microprocessor architectures. The architecture described consists of a RISC core controlled by a lookup microcode ROM. An external interface controller to emulate the exact behavior of all external interfaces was proposed. The RISC core would execute one instruction per clock cycle, and to maintain compatibility would generate no operation instructions for timing purposes. Register to memory. Register memory instructions allow memory words to be fetched into registers where they can be used as ALU inputs in subsequent instructions. Register instructions fetch two operands from the registers into the ALU input registers, perform operations on them, and put the results back into a register. Memory instruction fetches its operands from memory into the ALU registers, performs its operation, and stores the results back into memory. Opcode decode. The instruction stored in the instruction register is then decoded. The operation code, opcode, in the instruction gives information on what the instruction is supposed to do. This opcode is then used to point to a particular address in the microcode ROM, which then issues relevant signals for controlling various functions like the ALU, stack, bus interface unit, register file, and interrupt mechanism. Priority encoder. The microprocessors studied have the following control pins and interrupt modes that affect the operations of the CPU. The microprocessor may be in a particular operation mode at any given time. It can be in the run mode, reset mode, interrupt mode, etc. The next instruction to be executed depends upon the mode in which the microprocessor is. The program counter is loaded with a particular value depending upon this mode. The microprocessor state can be determined by using a priority encoder. The inputs to the encoder are the control pins as well as the external interrupt signals. The priority encoder encodes the priority of the signal available at that particular pin and makes it available at the output. A signal at a higher priority masks out signals with lower priority so that only the highest priority signal is encoded at the output. These priorities can be configured as per specific needs. The priority encoder may be modified to store the signal requests into latches so that they may be implemented once all of the higher priority requests are attended to. 8086 microprocessor. The 8086 is a 16-bit microprocessor chip designed by Intel between early 1976 and mid-1978 when it was released. The 8086 microprocessor gave rise to the x86 architecture. It eventually turned out to be Intel's most successful line of processors. The x86 design. The 8086 project started in May 1976 and was originally intended as a temporary substitute for the ambitious and delayed IAPX 432 project. It is sequenced using a mixture of random logic and microcode and was implemented using depletion load and NMOS circuitry with approximately 20,000 active transistors. Marketed as source compatible, the 8086 was designed to allow assembly language for the 8008, 8080, 8085 to be automatically converted into equivalent 8086 source code with little or no hand editing. The legacy of the 8086 is enduring in the basic instruction set of today's personal computers and servers. The 8086 also lent its last two digits to later extended versions of the design, such as the Intel 286 and the Intel 386, all of which eventually became known as the family x86. Buses and operation. All internal registers as well as internal and external data buses were 16 bits wide, firmly establishing the 16-bit microprocessor identity of the 8086. A 20-bit external address bus gave a 1 MB physical address space. This address space was addressed by means of internal segmentation. Some of the control pins which carry essential signals for all external operations had more than one function, depending upon whether the device was operated in min or max mode. The former extended for small single processor systems, while the latter was for medium or large systems using more than one processor. Registers and instructions. The 8086 has 8 more or less general 16-bit register. 4 of them, AX, BX, CX, and DX, could be assessed as twice as many 8-bit registers, while the other 4, BP, SI, DI, and SP, were 16-bit only. The 8086 is also featured with 64 KB of 8-bit input or output space. A 64 KB stack growing towards lower address is supported in hardware. 2-byte words are pushed to the stack, and the stack is pointed to by SS is to SP. There are 256 interrupts, which can be invoked by both hardware and software. The interrupts can cascade using the stack to store the return address. 8088 microprocessor. The Intel 8088 microprocessor is a variant of the Intel 8086. Introduced on July 1, 1979, the 8088 had a bit external data bus instead of the 16-bit bus of 8086. The 16-bit registers and the 1 megabyte address range were unchanged, however. In fact, according to the Intel documentation, the 8088 and 8086 have the same execution unit. Only the bus interface unit is different. The original IBM PC was based on the 8088. History and description. It was designed in Israel at Intel Haifa Laboratory with a large number of Intel processors. The 8088 is targeted at lowering costs by allowing the use of an 8-bit path and 8-bit support and peripherals chip. Complex circuit boards were still fairly heavy to carry or to use and also were expensive when 8088 was released. The prefetch queue of the 8088 was shortened to 4 bytes from the 8086 to 6 bytes, and the prefetch algorithm was slightly modified to adapt to the narrower bus. These modifications of the basic 8086 design were one of the first jobs assigned to Intel's then new design office and laboratory in Haifa, Israel. The Intel 80286 was introduced on 1 February 1982. It is a 16-bit x86 microprocessor with 134,000 transistors. Like its contemporary, it is simple. The 80186 can correctly execute most software written for the earlier Intel 8086 and 8088. It was employed for the IBM PCA introduced in 1984 and then widely used in most PCA-compatible computers until the early 1990s. The 80286 was the first x86 microprocessor with memory management and wide protection abilities. History. Initial release starts after the 6 or 8 MHz. It was subsequently scaled up to 12.5 MHz. On average, the 80286 has a speed of about 0.21 instructions per clock. The 6 MHz model operated at 0.9 MIPS, the 10 MHz model at 1.5 MIPS, and the 12 MHz model at 2.66 MIPS. The later E-stepping level of the 80286 was free of the several significant errata that caused problems for programmers and operating system writers in the earlier B-step and C-step CPUs. Architecture. The 80286 was designed for multi-user systems with multitasking applications, including communications and real-time process control. It had 134,000 transistors and consisted of 4 independent units: address unit, bus unit, instruction unit, and execution unit. These were organized into pipeline, significantly increasing performance. It was produced in a 68-pin package, including PLCC, plastic leaded chip carrier, LCC, leadless chip carrier, and PGA, pin grid array packages. The performance of the 80286 per clock cycle exceeded that of the Intel 8086 and Intel 8088 by more than 2 times. This increase of the 80286's performance over its immediate predecessors may be the largest among the generation of x86 processors. The Intel 80286 had a 24-bit address bus and was able to address up to 16 MB of RAM compared to 1 MB for its predecessor. However, cost and initial rarity of software using memory above 1 MB meant that 80286 computers were rarely shipped with more than 1 megabyte of RAM. 80386 microprocessor. The Intel 80386 referred as the Intel 386, i386 or just 386, was a 32-bit microprocessor introduced by Intel in 1985. The first versions had 275,000 transistors and were used as a central processing unit of many workstations and high-end personal computers of the time. As the original implementation of the 32-bit extension of the 8086 architecture, the 80386 instruction set, programming model, and binary encodings are still the common denominator for all 32-bit x86 processors. This is termed x86, IA32, or i386 architecture, depending on the context. The 80386 could correctly execute most code intended for earlier 16-bit x86 processors, such as the 8088 and 80286 that were ubiquitous in early PCs. The 80386 was launched in October 1985, but full-function chips were first delivered in the third quarter of 1986. Main boards for 80386-based computer systems were cumbersome and expensive at first, but manufacturing was rationalized upon the 80386 mainstream adoption. The first versatile computer to make use of the 80386 was designed and manufactured by Compaq and marked the first time a fundamental component in the IBM PC-compatible de facto standard was updated by a company other than IBM. Architecture. The processor was a significant evolution in the x86 architecture and extended a long line of processors that stretched back to the Intel 8008. The predecessor of the 80386 was the Intel 80286, a 16-bit processor with a segment-based memory management and protection system. The 80386 added a 32-bit architecture and a paging translation unit, which made it much easier to implement operating systems that used virtual memory. It also offered support for register debugging. The 80386 featured 3 operating modes: real mode, protected mode, and virtual mode. The protected mode, which debuted in the 286, was extended to allow the 386 to address up to 4 GB of memory. The all-new virtual 8086 mode made it possible to run one or more real mode programs in a protected environment, although some programs were not compatible. The 32-bit flat memory model of the 386 would arguably be the most important feature change for the x86 processor family until AMD released x86-64 in 2003. Chief architect in the development of 80386 was John H. Crawford. He was responsible for extending the 80286 architecture and instruction set to 32-bit and then led the microprogram development for the 80386 chip. The 80486 and P5 Pentium line of processors were descendants of the 80386 design. Chip variants. There are 2 types of variants. They are i386SX variant and i386SL variant. i386SX variant. In 1988, Intel introduced the i386SX, a low-cost version of the 80386 with a 16-bit data bus. The CPU remained fully 32-bit internally, but the 16-bit bus was intended to simplify circuit board layout and reduce total cost. The 16-bit bus simplified designs but hampered performance. Only 24 pins were connected to the address bus, therefore limiting addressing to 16 MB, but this was not a critical constraint at that time. Performance differences were due not only to differing data bus widths, but also due to performance-enhancing cache memories, often employed on boards using the original chip. The original 80386 was subsequently renamed i386DX to avoid confusion. However, Intel subsequently used the DX suffix to refer to the floating point capability of the i486DX. The i387SX was an i387 part that was compatible with the i386SX. The 386SX was packaged in a surface mount QFP and sometimes offered in a socket to allow for an upgrade. i386SL variant. The Intel 80486 was a higher performance follow-up to the Intel 80386 microprocessor. Introduced in 1989, it was first tightly pipelined x86 design, as well as the first x86 chip to use more than 1 million transistors due to a large on-chip cache and an integrated floating point unit. It represents a fourth generation of binary-compatible CPUs since the original 8086 of 1978. A 50 MHz 80486 executed around 40 million instructions per second on average and was able to reach 50 MIPS peak performance. The i486 was without the usual 80 prefix because of a court ruling that prohibited trademarking numbers. Later, with the introduction of the Pentium brand, Intel began branding its chips with words rather than numbers. Architecture. The instruction set of the i486 is very similar to its predecessor, the Intel 80386, with the addition of only a few extra instructions, such as CMPXCHG, which implements a compare and swap atomic operation, and XADD, a fetch and add atomic operation, returning the original value. From a performance point of view, the architecture of the i486 is a vast improvement over the 80386. It has an on-chip unified instruction and data cache, an on-chip floating point unit FPU, and an enhanced bus interface unit. Due to the tight pipelining, sequences of simple instructions could sustain a single clock cycle throughput. These improvements yielded a rough doubling in integer ALU performance over the 386 at the same clock rate. A 16 MHz 486 therefore had a performance similar to a 33 MHz 386, and the older design had to reach 50 MHz to be comparable with a 25 MHz 486 part. Models. There are several suffixes and variants. Other variants include Intel Rapid CAD, i486SL, and i486 Overdrive. 80387 Microprocessor. x87 is a floating point related subset of the x86 architecture instruction set. It originated as an extension of the 8086 instruction set in the form of optional floating point coprocessors that worked in tandem with corresponding x86 CPUs. These microchips had names ending in 87. This was also known as the NPX numeric processor extension. Like other extensions to the basic instruction set, x87 instructions are not strictly needed to construct working programs, but provide hardware and microcode implementations of common numerical tasks, allowing these tasks to be performed much faster than corresponding machine code routines. Floating point operations: addition, subtraction, comparison, complex numerical operations. The x87 instruction set includes instructions for basic floating point operations such as addition, subtraction, and comparison, but also for more complex numerical operations such as the computation of the tangent function and its inverse. Architectural generations. 8087. The 8087 was the first math coprocessor for 16-bit processors designed by Intel. It was built to be paired with Intel 8088 or 8086 microprocessors. 80187. The 80187 was a math coprocessor for Intel 80186 CPU. It is incapable of operating with the 80188, as 80188 has an 8-bit data bus. The 80188 can only use the 8087. The 80187 did not appear at the same time as the 80186 and 80188, but was in fact launched after the 80287 and the 80387. Although the interface to the main processor was the same as that of the 8087, its core was that of the 80387 and was thus fully IEEE 754 compliant, as well as capable of executing all the 80387's extra instructions. 80287. The 80287 I287 was a math coprocessor for the Intel 80286 series of microprocessors. Intel's models included variants with specified upper frequency limits ranging from 6 up to 12 MHz. Later followed the i80287XL with 387 microarchitecture and the i80287XLT, a special version intended for laptops, as well as other variants. The 80287XL was actually an 80387SX with a 287 pinout. It contained an internal 3x2 multiplier, so that the motherboards which ran the coprocessor at 2x3 CPU speed could instead run the FPU at the same speed of the CPU. Other 287 models with 387-like performance were the Intel 80C287, built using CHMOS3, and the AMD 80EC287, manufactured in AMD's CMOS process using only fully static gates. The 80287 and 80287XL worked with the 80386 microprocessor and were initially the only core processors available for the 80386 until the introduction of the 80387 in 1987. 80387. The 80387-387 or i387 was the first Intel core processor to be fully compliant with the IEEE 754 standard, released in 1987, a full 2 years after the 386 chip. The i387 included much improved speed over Intel's previous 8087, 80287 core processors and improved the characteristics of trigonometric functions. Without a core processor, the 386 normally performed floating-point arithmetic through software routines implemented at runtime through a software exception handler. When a math core processor is paired with the 386, the core processor performs the floating-point arithmetic in hardware, returning results much faster than a software library call. 80487. The i487SX was marketed as a floating-point unit core processor for Intel i486SX machines. It actually contained a full-blown i486DX implementation. When installed into an i486SX system, the i487 disabled the main CPU and took over all CPU operations. Direct Memory Access (DMA). Devices wishing to perform DMA assert the processor's bus request signal. Processor completes the current bus cycle and then asserts the bus grant signal to the device. The device then asserts the bus grant acknowledge signal. The processor senses a change in the state of bus grant acknowledge signal and starts listening to the data and address bus for DMA activity. The DMA device performs the transfer from the source to destination address. During these transfers, the processor monitors the addresses on the bus and checks if any location modified during DMA operations is cached in the processor. If the processor detects a cached address on the bus, it can take one of two actions. Processor invalidates the internal cache entry for the address involved in DMA write operation. Processor updates the internal cache when a DMA write is detected. Once the DMA operations have been completed, the device releases the bus by asserting the bus release signal. Processor acknowledges the bus release and resumes its bus cycles from the point it left off. Interrupt handling. Here we describe interrupt handling in a scenario where the hardware does not support identifying the device that initiated the interrupt. In such cases, the possible interrupting devices need to be polled in software. A device asserts the interrupt signal at a hardwired interrupt level. The processor registers the interrupt and waits to finish the current instruction execution. Once the current instruction execution is completed, the processor initiates the interrupt handling by saving the current register contents on the stack. The processor then switches to supervisor mode and initiates an interrupt acknowledge cycle. No device responds to the interrupt acknowledge cycle, so the processor fetches the vector corresponding to the interrupt level. The address found at the vector is the address of the interrupt service routine. The ISR polls all the devices to find the device that caused the interrupt. This is accomplished by checking the interrupt status registers on the devices that could have triggered the interrupt. Once a device is located, control is transferred to the handler specific to the interrupting device. After the device-specific ISR routine has performed its job, the ISR executes the return from interrupt instruction. Execution of the return from interrupt instruction results in restoring the processor state. The processor is restored back to user mode. Interrupt acknowledge cycle. Here we described interrupt handling in a scenario where the hardware does support identifying the device that initiated the interrupt. In such cases, the exact source of the interrupt can be identified at hardware level. A device asserts the interrupt signal at a hardwired interrupt level. The processor registers the interrupt and waits to finish the current instruction execution. Once the current instruction execution is completed, the processor initiates the interrupt handling by saving the current register contents on the stack. The processor then switches to supervisor mode and initiates an interrupt acknowledge cycle. The interrupting device responds to the interrupt acknowledge cycle with the vector number for the interrupt. Processor uses the vector number obtained above and fetches the vector. The address found at the vector is the address of the interrupt service routine, ISR, for the interrupting device. After the ISR routine has performed its job, the ISR executes the return from interrupt instruction. Execution of the return from interrupt instruction results in restoring the processor state. The processor is restored back to user mode. Synchronization requirements for DMA and interrupts. Many times software designers have to work with data structures that are shared with interrupts or DMA devices. This requires performing atomic updates to the shared critical regions. Synchronization with interrupts. When a data structure is shared with an ISR, disabling the interrupt to execute the critical region updates is a good technique. Keep in mind that disabling of interrupts should be restricted to only the code that updates the critical region. Keeping the interrupts disabled for a long time will increase the interrupt latency. Another option is to make use of the fact that interrupts are processed at instruction boundaries. A single instruction that performs read as well as write could be used to perform an atomic transaction. For example, if your processor supports direct memory increment, you could increment a shared semaphore without disabling interrupts. Synchronization with DMA. Sharing data structures with a DMA device is tricky. The processor can initiate a DMA operation at a bus cycle boundary. This means that a new DMA operation can be started in the middle of an instruction execution. Keep in mind that an instruction execution involves multiple bus cycles. The best mechanism to perform critical region updates is to use a read, modify, write bus cycle. With this instruction, atomic updates can be made to critical regions as the read and write are glued together in a special bus cycle. Another option is to disable DMA operation. Extreme caution should be used when employing these techniques. Some processors also support disabling DMA operations by using locked bus cycles. The processor could execute lock instructions to disable external bus grants. When critical region updates have been completed, the unlock instructions is used to allow bus grants. Another mechanism to prevent DMA might be to temporarily disable the device that will perform DMA. For example, if the DMA operations are being performed by an Ethernet controller, disabling the Ethernet controller will make sure no DMA operations are started when a critical region update is being made. 8086 architecture set. The microprocessor functions as a CPU in the stored program model of the digital computer. Its job is to generate all system timing signals and synchronize the transfer of data between memory, I/O, and itself. It accomplishes this task via the 3-bus system architecture set. The microprocessor also has an SW function. It must recognize, decode, and execute program instructions which are fetched from the memory unit. This requires an arithmetic logic unit, ALU, within the CPU to perform arithmetic and logical AND, OR, NOT, compare, etc. functions. The 8086 CPU is organized as 2 separate processes called the Bus Interface Unit, BIU, and the Execution Unit, EU. The BIU provides HW functions, including generation of the memory and I/O addresses for the transfer of data between the outside world, outside the CPU, and the EU. The EU receives program instruction codes and data from the BIU, which executes these instructions and stores the results in the general registers. By passing the data back to the BIU, data can also be stored in a memory location or written to an output device. EU has no connection to the system buses. It receives and outputs all its data through the BIU. The only difference between 8088 microprocessor and an 8086 microprocessor is a BIU. In the 8088, the BIU data bus path is 8 bits wide, whereas the 8086 is a 16-bit data bus. Another difference is that the 8088 instruction queue is 4 bytes long instead of 6. The important point to note, however, is that the EU is the same for each processor. The programming instructions are exactly the same for each. Programs written for the 8086 can be run on the 8088 without any changes. 8088 architecture set. Intel 8088 includes two main sections, the execution unit and the bus interface unit. The EU takes care of the processing, including arithmetic and logic. The BIU controls the passing of information between the processor and the devices outside the processor, such as memory, I/O ports, storage devices, etc. The purpose of the different portions of the processor within these two units. Instruction set of 8086 microprocessor. An instruction set is a binary pattern designed inside a microprocessor to perform a specific function. The entire group of instructions that a microprocessor supports is called instruction set. 8086 has more than 20,000 instructions. Classification of instruction set. There are various types of instruction set. They are data transfer instructions, arithmetic instructions, bit manipulation instructions, program execution transfer instructions, string instructions, processor control instructions. Data transfer instruction set. These instructions are used to transfer data from source to destination. The operand can be a constant memory location, register, or I/O port address. Move destination source. Source operand can be register, memory location, or immediate operand. Destination can be register or memory operand. Both source and destination cannot be memory location at the same time. Example: move CX 037AH, move AL, BL, move BX 0301H. Push operand. It pushes the operand into top of stack. Example: push BX. IN accumulator port address. It transfers the operand from specified port to accumulator register. Example: INAX 0028H. Arithmetic instruction set. NEG source. It creates 2's complement of a given number. That means it changes the sign of a number. Division source. It is an unsigned division instruction. It divides word by byte or double word by word. The operand is stored in AX, divisor is source, and the result is stored as AH equals remainder, AL equals quotient. Bit manipulation instructions. These instructions are used at the bit level. These instructions can be used for testing a 0 bit, set or reset a bit, shift bits across registers. Program execution transfer instruction set. These instructions cause change in the sequence of the execution of instructions. This change can be through a condition or sometimes unconditional. The conditions are represented by flags. String instruction set. String in assembly language is just sequentially stored bytes or words. There are a very strong set of string instructions in 8086. By using these string instructions, the size of the program is considerably reduced. Instruction set of 8088 microprocessor. Instruction set of 8088 processor consists of the following instructions: data moving instructions, arithmetic instructions, add, subtract, increment, decrement, convert, byte, word, and compare. Logic instructions, AND, OR, exclusive, OR, shift, rotate, and test. String manipulation instructions, load, store, move, compare, and scan for byte, word. Control transfer instructions, conditional, unconditional, call subroutine and return from subroutine. Input-output instructions, other, setting, clearing, flag bits, stack operations, software interrupts, etc. Steps for program development. The steps to program development are: system analysis, specification and design, program, debug, alpha test, beta test, deliver the software. System analysis. System analysis involves creating a formal model of the problem to be solved. The model is created by enabling the user to access their needs, understanding the complete problem that is to be solved, making a formal representation of a system being designed. Specification and design. At this stage, a detailed design is written which defines the data structure, user interface, inputs, outputs, and algorithms. Data structure. It defines the type of formal data used in programming. User interface. It refers to the screen through which the user enters the data and displays that data. Inputs. It defines the kind of data which is entered in the program. Output. It is the data which is displayed on the screen. Algorithms. It is the method of calculating the output which depends upon the input. Program. Programmers use a specification to write a program code which is necessary for a program. The code is useful in compiling the program. Future maintenance, code reliability, and documentation are very important for the program. Debug. Defect in program is called as debug. These faults are eliminated to run a program without an error. Errors are created by programmers. Alpha test. It is a trial program. Program shows us the needs and user interface. Any errors in the code and specification will be corrected during the alpha stage. Beta test. This is the second range of tests which is conducted after alpha test. In this stage, the remaining bugs are cleared, those which are not detected during the alpha test. Software delivery. The completed software is packaged with full documentation and delivered to the end users. Testing for developed program. Issues in microprocessor testing, large number of registers, large number of small buffers or queues, different sizes of memories, complex random logic, control path and data path, board level testing, test integration and scheduling, CAD tool support. Systems with microprocessor. A system is an organization of components, hardware, software parts, and subsystems with capability to perform useful functions. Systems with a microprocessor can use it to implement testing strategies for the whole system. Functional testing. It verifies the integrity of a system. There are two types. They are without using fault model and using a specific fault model. Features of 80386. There are two versions of 80386 which is commonly available. 80386DX, 80386SX. 80386DX. It has 32-bit address and 32-bit data bus packaged with 132-pin ceramic pin grid array and address 4 GB of memory. 80386SX. It has two types of data bus, 24-bit address bus and 16-bit data bus. The package is 100-pin flat with 16 MB of memory. Features in microprocessor. The 80386SX was developed after the DX for application that didn't require the full 32-bit bus version. It is found on many PCs and uses the same basic motherboard design as the 80286. Most applications require less than 16 MB of memory. The SX is popular as the less costly version of the 80386 microprocessor, 20 to 33 MHz frequency, 4 levels of protection, paging, virtual memory and memory management section supports. The 80386 CPU supports 16K number of segments and thus total virtual memory space is 4 GB into 16K equals 64 terabytes. The data buffers interface the internal bus with the system bus. The 80386 enters the virtual 8086 mode within the protection mode. This is to be set only when the 80386 is in protected mode. In this mode, if any privileged instruction is executed, an exception 13 is generated. This bit can be set using IRET instruction or any task switch operation only in the protected mode. Also, it is not automatically cleared after the successful execution of JMP, call, and INT instruction, causing a task switch. These instructions are used to set the RF to the value specified by the memory data available at the stack. The 80386 has 5 types of descriptors listed as follows: code or data segment descriptors, system descriptors, local descriptors, TSS, task state segment descriptors, gate descriptors. The 80386 provides a 4-level protection mechanism exactly in the same way as 80286 does. Paging. Paging is a memory management technique which is used for virtual memory multitasking unit. Physical type memory is divided into a variable size segment, whereas the paging is into fixed size pages. Virtual 8086 mode. It is protected mode of operation which operates and executes as 8086 programs. The real mode is used to execute the 8086 programs, which is capable of protection and few additional instructions. If the 80386 enters a protected mode from the real mode, it cannot return back without reset operation. Thus, an operation is made to execute the programs in protected mode. The address forming mechanism in virtual mode is exactly identical with that of real mode. Version of 80486. Intel's i486SX was a modified Intel 486DX microprocessor with its floating point unit FPU disabled. All early 486SX chips were actually i486DX chips with a defective FPU. If testing showed that the central processing unit was working but the FPU was defective, the FPU's power and bus connections were destroyed with a laser and the chip was sold cheaper as an SX. If the FPU worked, it was sold as a DX. Computer manufacturers that use these processors include Packard Bell, Compaq, and IBM. Back in the early 1990s, common wisdom held that it wasn't advantageous for most users to have an FPU. Thus, many typical household applications already in existence, like word processing and email, were designed specifically to avoid using floating point operations. When floating point operations needed to be performed, they were still performed, but not in hardware. Instead, the operations were usually facilitated by transparent software emulation. Some systems allowed the user to upgrade the i486SX to CPU with a FPU. The FPU upgrade device was shipped as the i487, which was a full-blown i486DX chip with an extra pin. The i487 was installed in an upgrade socket, and the extra pin was either a power or ground pin that indicated that the i487 was installed. That signal was used to disable the i486SX when the i487 was installed. Although i486SX devices were not used at all when the i487 was installed, they were hard to remove because the i486SX was typically installed in non-ZIF sockets or in a plastic package that was surface mounted on the motherboard. Limitations of 80286 that led to 80386. It has only 16-bit processor. Maximum segment size is 64 KB. It cannot be switched between real mode and protected mode. Resetting is required. Addressable memory is 16 MB. It is useful to increase the system performance. 80386 is a 32-bit microprocessor which was produced in 1985. It contains 132 pins and 129 instructions. The execution is pipelined and operation is multitasking. It will also run on 386 microprocessor. Improvements made in 80486 over 80386. It is a coprocessor integrated on the chip and allows executing the program faster. It uses 4-way Z-associated cache. Some include main cache, which is empowered with a 8 KB cache memory. Comparison. They are the technical names for what are usually called the 386 and 486 processors. The original computer process used in PCs was called the 8086. It was upgraded to the 80286 or 286. It was the first computer processor capable of running a version of Windows 3.0. Working. The 386 came on the market around 1994 and is a dinosaur by today's standards. It could run Windows 3X, 95, 98 and ME but nothing better. The 486 came out about 3 years later. It was faster than a 386. It could usually handle Windows 2000 and XP as well as the 9X versions of Windows. Conclusion. In this chapter, the users have covered the following aspects of introduction to microprocessors microcomputer. Introduction to digital computer, microcomputer organization, machine language, architecture of a 16-bit generic microprocessor, simplified memory organization, DMA, interrupts, 8086-8088 architecture and instruction set, steps for program development for 8086-8088, features of microprocessor, introduction to 80286, 80386, 80486, numeric processor 80387, various versions of 80386 and 80486, like 80386SX, 80386DX, 80486SX, 80486DX2, 80486DX4, and their comparisons.